There's not that many people here, right? We could probably just do this without a mic. Do you think? We could just do the one mic. Let's do this. Okay, well, welcome everybody. Thanks for coming out tonight. Hopefully folks on YouTube can hear us. Let's have a look. Let's have a look. Let's see. Okay, perfect. Excellent. Okay. Yeah, well, thanks for coming out. We're really excited about tonight. We've got a really excellent speaker. I think you're really going to enjoy that. So for those of you who've never been here to one of these events, this is the First Friday Astronomy hosted by Boise State Physics. I'm Brian Jackson, a professor here in the physics department, teach astronomy, among other things. This is a monthly event that takes place on the first Friday of every month. And we do it all throughout the year, even if school is out of session. We still make our students come down and work the event. So feel free, please join us every month. If it's a first Friday of the month, there's going to be one of these events. They always start at 7:30. They run about an hour. If the weather's clear, we do stargazing afterward. I think it's going to be cloudy tonight, so we probably won't be able to do stargazing. But if you want to stick around and go visit the observatory on top of this building, there's a really beautiful view up there of the cityscape. So you're welcome to stick around after the talk and see that. In addition to the observatory on top of the building here, we have a planetarium, which many of you probably walked past. And so if you haven't had a chance to check that out, be sure to check that out on the way out. These events are 100% supported by public donations. And so if this is something you'd like to support, feel free to visit the website here. You can donate, and that'll link you directly to the donation website to support these events. Let me also introduce Mr. Benjamin Satterwhite, who also has an event that we'd like you to be invited to.
Yeah, we're really excited. So my name is Benjamin Satterwhite. I'm the director of the around for a while. We recently just renovated it, and we're trying to get some new public outreach. Oh,
it occurs to me. Let me.
Yeah. Let me get on this thing. All right, cool. Oh, I'll even step up here. Oh, is it going to follow me around? All right, cool. Yeah. So I'm the director of the Julius Checker Planetarium. Also teach astronomy at Capitol High School. And our goal is to maybe add in a third Thursday public planetarium show. So we're going to give it initial run through this month. It's going to be on April 21st. I think we are shooting for 7:30. We got about 45 to 50 seats. So it's first come, first serve. All are welcome. I think we're just going to do a little donation at the front. And I think we're going to hold off on the observing as well. Just for the timing aspects of things, but we're going to be checking out local stargazing stuff that we can see for the next month. Probably try to do some topical stuff as well. So all are welcome, and we're really excited to kind of provide another service for the public. So really excited to work and collaborate with these guys.
Yeah, thanks. All right, perfect. Yeah, so that'll be a lot of fun. Join us April 21 out at Capitol High School. We have of course, as I said, we do this every month, and we have our summer season coming up. And I just wanted to pitch that to you a little bit, be a sneak preview. I mean, not so sneaky. Here's our summer season. So we've booked it all out each month, first Friday of every month, 7:30. In May, we're going to have a friend of mine, Dr. Christy Swan. She's an expert in aeolian transport. So these are the processes in a planetary atmosphere that transport dust and sand. It should be fascinating. She does these really cool experiments on the beach in North Carolina in hurricanes. So it should be a really neat talk. June 3rd, we have Dr. Andres Salsado, who does galactic cluster lensing, gravitational lensing. That should be fascinating. Dr. Alejandro Soto, in July, we'll be talking about his work on Martian dust storms. And then at the end of the summer, we'll have Dr. Katie Devine, who's a local here. She teaches at College of Idaho. She's a really excellent astronomer. She's going to talk about her work looking at star formation. So as always, these events are going to start 7:30, 8:30. Well, you know, here in the summer, the sun doesn't really go down until 10:30. So it'll be late if we do stargazing, but you're certainly welcome to stick around for those. And I should say as well, these events are of course happening in person, but they are also live streamed. So we're actually on YouTube right now being live streamed and recorded. So if ever you just can't make it out for one night, visit boi.st. So for Boise State, boi.st/astrobroncos live, and it'll take you directly to the YouTube live stream that you can watch. Okay, let's get out of this. Back up, perfect. Okay, and with that, I would like to introduce our speaker for this evening. Our speaker is Dr. Erin Cox. Dr. Cox is a Sierra, is it a Sierra Fellow? Is that what the current position is? Sierra Fellow, and soon to be an NSF postdoctoral fellow at Northwestern University. She has done a lot of really interesting research, which you hear about tonight. But one thing that she was just telling me about, I think which is particularly interesting, she works with the Northwestern prison education program. And so this is a program in Illinois that grants degrees to prisoners. She got a bachelor's degree at the University of Arizona in Tucson, and then a PhD from the University of Illinois. We just had a really fantastic time visiting with her this week and learning all about her research. And so now you will too. And with that, let's welcome Dr. Erin Cox. I can turn the lights. You want the lights off? Or is this,
is there like maybe a halfway point?
just switches back and do things to the lights.
Yeah, I think that. But yeah, I mean, so I think that makes that image stand out pretty nicely. I think that's the only one that really needs like dimming. Yeah, so thank you for having me. It's been a pleasure. So this is my first time in Boise. And I've enjoyed my visit so far. This is also my first time giving a talk in person in over 2.5 years. So hopefully not too rusty at it. Tonight I'm going to be telling you about some research I've done and some colleagues of mine that involves planet formation. But first, I am an observational astronomer. Which means that I get data from telescopes and I analyze this data and I make scientific predictions based on this data. I don't always get to go to telescopes. So a lot of people might have this idea that if you're an observer, you're actually sitting down in this room at the telescope and looking at what the telescope's bringing in, but that's not really what we do so much anymore. But I have had the opportunity to go to a few telescopes, mostly in grad school. So up here, there we go. So here I am after an observing run. So after 10 hours of observing on the Mauna Kea summit in Hawaii. So these white domes here are the Keck telescope down in Hawaii. I didn't get to observe on that, but my telescope operator drove me up to see these. These are the telescopes that we learned about in school. So it was really exciting to be able to go and actually see them in action. Over here on the right, I took a summer school at the Karma Interferometer. So this is a radio array. I will talk to you more about what that means in a few minutes. But this was an opportunity for me to learn how to do radio astronomy. Unfortunately, this telescope is no longer running, but it was a great experience. And then finally, what I often think is maybe one of the coolest experiences is I actually got to fly on the Sophia telescope here. So this is a Boeing 747 jet. You can see that there is a hole cut out of this airplane. And that's where the telescope is actually doing its observations. So this is me on the plane. This is actually some data that was taken for my PhD thesis. It was kind of a trip. So the whole observing time, like you have like maybe 10 hours of nighttime, depending on what time of year it is. So you go up in this jet at around sunset and you take this 10-hour flight. So you're essentially on like an international flight, but you start and stop in the same spot. So it's in Palmdale, California. It's about an hour east of Los Angeles. And it was a really exciting and fun experience, and unlike anything that I've done before. And the telescope has a whole suite of people who work specifically for it. They're behind me doing Something important, probably aligning the mirrors, checking to make sure everything's running properly. Great. So when we think about our own solar system, we think about, probably like Earth and what it means to have life on Earth. But maybe what you're not thinking about is how diverse our solar system is. So we have shown here on the top left, these are the 4 terrestrial planets. So these are accurate to their size. So we have these 4 small rocky planets, and then we have these big planets, so characterized by the gas giants, Jupiter and Saturn, and then Uranus and Neptune. And we see lots of variation in the composition of these planets in our own solar system and what their sizes are. And then we also see, this is now accurate to the orbits. You can't actually have an accurate size and accurate orbits. It doesn't really work out because the sun is just way too big. But these are accurate to the orbit. So we see the terrestrial planets are close in to the sun, and then it starts getting spaced out. So we can begin to ask ourselves is the solar system common? Like, should we expect to see these same types of planets surrounding other stars? And the answer to that, at least how it seems now, is that our solar system is actually not that common. So this is a plot. You don't have to take away everything this plot is showing you. But what I want you to notice, so on this y-axis here is planet mass versus orbital period. So how long it takes the planet to orbit its star. So it takes Earth 1 year, right? So we've put on here the planets of our solar system that will fit. So Mercury doesn't fit on here, unfortunately. And what you see is that the solar system planets don't really occupy the same space that the exoplanets occupy. So these are all, these are 4,300 exoplanets. So this was from a 2021 paper showing all 4,300. And you see that they're not in the same spot. So we can look at it a different way. We can look at how big the planets are. So here we're plotting the planet's radius. It's normalized to Earth radii. Astronomers like to normalize to like what we know. So we like to say Earth masses, 1 AU is like the distance from the Earth to the sun. So we just like to quantify things like that. So here we see, again, the solar system planets are not occupying the same space that the exoplanets are. And we can ask ourselves, why is that? Well, maybe we just haven't observed enough exoplanet systems to find one like our own solar system. But we've looked at over 5,000 planets. So the plot from the slide before only had 4,300. Just this last week, NASA announced that we've actually observed 5,000 planets. And this is kind of a census of the types of planets that we found. So about a third gas giants, another third these so-called super Earths. So they're we don't have an analog in our own solar system. They are planets that are bigger than Earth, smaller than Neptune, but we don't really have one. And then we have some Neptune-like planets, and then we do have terrestrial planets that we found. But these terrestrial planets are around really, really small stars. So we have yet to find a solar system analog. So it seems, at least right now, that we are not a common outcome of planet formation. And why is that? Well, to start to answer these questions, I mean, I won't lie to you, we don't actually know the answer to those questions just yet. But to start to answer these questions, we look to where planets form. And they're in these protoplanetary disks. So this is an artist's impression of what a protoplanetary disk might look like. So you have this central star here. You have all this stuff. It's gas, dust, ice, things like that. You have maybe these protoplanets or planets that have formed. Maybe you can see here, there's some like maybe pebbles, some larger rocky bodies. So these are the types of disks that we need to look at to really understand how planets form. And then maybe begin to understand why we seem to be an uncommon outcome. So planet formation starts in the hearts of molecular clouds. So this is the pillars of creation taken by the Hubble Space Telescope in two different ways of looking at light. So on the left here, we see these three pillars in optical light, so the light you and I can see. And there are stars forming inside of these dusty clouds, but we can't really see through it. You can think of these clouds as the clouds we see in our atmosphere. So you can't see, usually you can't see behind those clouds. They block whatever's behind it. But if we look at these clouds through infrared light, whoops, shown here, you see a lot more stars. So as we go longer and longer in our wavelengths of light, we can start to pierce through these clouds and observe what's happening inside of them. Now, to the keen observer in the audience, you might notice that there's still these spots that are pretty opaque, even in the infrared. So that means we have to actually use longer wavelength telescopes to actually pierce through that dust. Okay, but this is just to illustrate how we can begin to look through these dusty clouds. So star formation and planet formation happen at the same time. And like I said on the last slide, they happen in the hearts of these cloud-like structures. So how big are these? Well, they range, they vary in size, just like anything does, but they're about a few parsecs in size. So a parsec is about 200,000 astronomical units. So an astronomical unit is abbreviated AU, and that is the distance from Earth to the sun. So these clouds are about 200,000 times the distance that we are from the sun. So they're pretty large. And inside of these clouds, we start to, they are made up of gas and really small dust particles, but they start to kind of form these like clumps of material, okay? And actually, when the clumps of material have accumulated enough mass, they become gravitationally bound. Gravitationally bound objects are roughly spherical in shape. So think of the sun, think of the planets in our solar system. They're all gravitationally bound and they're spheres. This is what we call the class 0 stage. And this is when star formation begins. This is like time equals 0 for the star. So I've shown here in this cartoon, it's maybe about 10,000 AU, this envelope surrounding this protostar. There's all this dusty gaseous material surrounding the protostar. And the star actually only has about 10% of the total mass that it will have once it's done forming. And you see here, indicated by the arrows, this just indicates that the material is raining down essentially onto the central star. And it turns out that as things start to accumulate and become gravitationally bound, they start to spin. So you start to get this spinning object. And as the material comes in from out here and goes onto the star, it will spin up. So you can think of this like the ice skater. If the ice skater is doing a turn and their arms are out, they are going at a slower speed than when they bring their arms in and they spin much faster. So this is called conservation of angular momentum. And we have to follow conservation of angular momentum because that's a physical law that the universe just follows. Well, it turns out that if we just let the material rain onto the star all by itself, the star will spin too fast and it'll rip itself apart but we know that they exist, that stars exist. And so a way to get around this is we actually, the stars can form a disk before the material falls onto the star. So this is the class 1 phase. So this is a little bit older than the class 0 phase. And we know that this is when most disks start to form in stars. And as time goes on, the disk becomes more massive. So the disk is actually what will feed the star all of the material that it will accumulate before it becomes a stellar system. And so you can maybe see here that this size scale has now changed. It's now down to about 100 AU in size. And this disk is much more massive by this point than here because all of this material has been funneled onto the disk. And if you go forward even further in time, then all of the disk starts to dissipate and you get a planetary stellar system. Okay, great. So exoplanets, like we saw at the beginning of this talk, are much easier to detect around sequence stars. So when I say main sequence, I just mean the time a star spends most of its life in. So if you want to equate that to a human, the average human spends most of its life in the adult stage, right? So this is like basically the star is an adult is what the main sequence is. And so we can detect exoplanets really pretty easily around stars like this. But when we're looking at stars as they're forming, it's really difficult to detect exoplanets because of how dusty the material is that's surrounding them. So we actually have only one verified protoplanet so far in all of this time of looking for these. But what we can use instead, I'm going to show you a video. It's going to go a little fast, but I'll slow it down after I've shown it, is we can use basically footprints in the disk to infer planet formation. So you see here, this is a nice smooth disk. Starts here. Let's get rid of these ads. Okay. So, and here is a Jupiter mass planet that's been put into this disk. And the person who ran this model let the disk just evolve. And what you can see over time, I'll fast forward a few seconds, is we get these ring-like structures in the disk. And that's just by virtue of putting a planet right there. So we can use these footprints to learn about the planets that are forming inside of the disks. Oops. So the previous generation of telescopes looked for these disks, and this is about what they found. So this is 6 protoplanetary disks. Shown here is again that 100 AU scale bar. This white blob here is basically the resolution of our observations. So the resolution being how fine of detail we can see. So we can't see any detail that is smaller than whatever the panel's little white blob shows. And the brightness, so the color scale just refers to the brightness. So if it's redder, it's brighter. If it's bluer, it's dimmer. So they're very centrally peaked, as we would expect. And you see here that they're kind of blobby, right? Yeah, there's not much going on. They're just kind of like little blobs, they're disks. But they don't look super exciting, except like what should be going on there. But yeah, So this is a blown up image on a different color scale of one of those disks that we saw. So this was taken using the Karma interferometer, which was one of the telescopes I showed earlier. So this is HL tau, and this was the best that we had at the time that this paper was published. And then Alma looked at it. So Alma came online about a decade ago And this was science verification data of Alma. So this is kind of the iconic protoplanetary disk that anyone who studies disks shows in their talk. So this image was released when I was a grad student, and it was exciting. I remember one of my friends was like, "Why are you so excited about this image? That's just a simulation." And I was like, "No, that is an actual image produced by a telescope." And what you see here, these dark concentric rings are those footprints that I told you a few slides ago that we should be on the lookout for when we're looking for active planet formation. So this was the first time that we had observational evidence that planet formation is occurring inside of these disks. That was exciting.
What's the wavelength?
So this is actually a combination of wavelengths. So it's at least 870 microns and 1.3 millimeters. I don't know if there was another wavelength that they added to this data. Oh, and I guess I forgot to say this is 10 minutes on source. So in 10 minutes, Alma was able to produce this image. So very powerful telescope. So here's the electromagnetic spectrum. So this is basically all light. So we go from radio waves to gamma rays. And this little bin here is the visible spectrum, which is what you and I can see. So you see that's very narrow in here. And like we discussed earlier in this talk, we can use longer wavelength observations to look through the dusty material of star forming regions. And in fact, what we actually use, which your question was a really good segue into this, is Alma operates about here. So this is on this image, it's called microwaves. We actually call it radio. I'm not exactly sure why they don't call it microwave astronomy, but radio astronomy is anything kind of this way of infrared. Yeah. So I told you that planet formation starts in disks, but we're scientists, so we want evidence for this. So some evidence that we can look for in our own solar system is by looking at objects that are in our sky. So this is a picture of the moon, Venus, and Jupiter. And you can see that these objects more or less are in the same plane. And so that was evidence for people that, you know, solar system objects must have evolved in a disk-like structure. The initial physical and chemical conditions of the planet of the disk can determine the composition of the planets. I put an asterisk there because it's only half true. You can have actually chemistry, different types of chemistry happening inside of the disk. So you can create different molecules than what you start off with. But pretty much what you start off with is more or less going to be like what you can end up with. And one thing is that maybe you know or don't know is that these planets have to form from the dust and gas that's in the disks. And the stuff that we start with is only about a micron in size. So the human hair is, I believe, a few nanometers in size. So nano to micro is about 2 orders of magnitude, so times 100. But we're talking about really, really, really tiny dust grains that somehow have to be built up into planets. Like the radius of the Earth is 6,000 kilometers. And the Earth is a pretty small planet. So we somehow have to get the dust from these micron-sized scales all the way up to a few thousand kilometers. So we do this by collecting the dust. So you can think of it if you have like a dusty floor and the dust kind of starts to come together, kind of forms these like dust bunnies. It's kind of fluffy, doesn't really have, it's airy, not much structure. But as the dust keeps hitting each other, it actually becomes compacted and will form these rocky pebble-like objects. And this actually becomes an issue because once you grow this dust to about 1 centimeter in size, so like a pebble, if you hit the dust or the pebble size rocks together, they don't like to stick together. They like to break apart and fragment. So we don't really know how to get past this, what we call centimeter barrier. But let's say that we did. So this is this image here. There's a lot going on here, but you don't have to worry about the words here. I just want to show you this because the disks surrounding protostars actually have some structure to them. So they're tall. They're not these infinitely thin disks. They actually have some height to them. And as the dust begins to grow, it actually settles in what we call the midplane of the disk. So larger dust is here and smaller dust is up here on like the top parts. Yeah. Yes, so the Kuiper belt, I think the most accepted theory is that it's like the leftover stuff from the disk. So it would be evolving during this time. And then as actually as the gas dissipates from the disk, whatever kind of rocky stuff is left over is what would be like the Kuiper belt objects we see in our solar system. And those are known as debris disks. So they're older than this, but they start here. Yeah, so you get this dust settling. And then in this midplane, you start to accumulate more mass, the little rocky bodies. But then you have this issue where when it's small dust grains and gas are really well coupled. And what I mean by that is you have these motions, everything's spinning, and the gas and dust are spinning together when the dust is still really small. But once the grains grow into these pebble-like objects and larger, they start to get pulled in towards the star. So we call that radial drift. And actually, once they reach about 1 meter in size, so like boulders, so like maybe like this big, they actually get pulled in to the star at a rate that is too fast for us to form planets. And so we have to somehow overcome this. So some really smart people came up with this idea that you can have these pressure bumps inside of the disks, so these gas bumps that can essentially trap the dust. So it traps the dust and the dust grows rapidly. And it's not able to escape these pressure bumps until a planetesimal has formed. So this is what we're seeing when we are looking at those footprints, those ring-like structures in the disk. We think we're seeing these pressure bumps where rapid dust growth is occurring. So to look at these objects, we utilize radio interferometers. So these are, I think, probably the two most common and two most famous interferometers. So this is the VLA, stands for Very Large Array. This is located in New Mexico, in Socorro, New Mexico, just outside of Albuquerque. And then the Alma telescope, which I've told you a little bit about, this is located in Chile, in the Atacama Desert, at about 15,000 feet. And so we use these in what's called interferometers. We call them that because they're essentially a collection of these radio dishes that are collecting the light from the objects that we're looking at. So in this case, protoplanetary disks. And they operate in the regime that we need to look at when we look at disks to understand more about it. So the reason I told you about the midplane is that these radio wavelengths can actually probe down. Let's go back a little bit. The radio wavelengths can actually probe down into this area, and we can understand what's happening right there when we use them. So some research that I've done is I took a snapshot survey of all of the what we call Premain sequence stars. So these are the class 2, maybe older class 1 stars in the Rho Fucus cloud. So this is located about 140 parsecs from Earth. And this was a very fast survey. So we only spent maybe 30 seconds, maybe shorter on each star. And everything here is plotted, like, so each little thing here, these are all the same scale. And that's so that you can see the diversity in scales. So I was really interested in looking at the demographics of these disks. So by demographics, I mean, how big are they? How bright are they? It's interesting to learn how bright they are because brightness is directly correlated with how massive they are. And so we want to know how massive these disks are, because if the planets are forming out of these disks, they can only accumulate as much material as what's in the disk, right? If you are making a snowman and you have just a little area of snow, you can't make a huge snowman. But if you have like an entire football field's worth of snow, you can probably make a few snowmen. They can be big, they can be small. You have a lot more options. So it's the same concept here. We want to know what types of planets we can form. And we actually had a really interesting discovery with this data set in that, so these are the isolated stars here. You see right off the bat, so this one, maybe average. These two are really big and bright. And a lot of these are really tiny, right? And they also show, so this one is at a different angle. It's maybe looking like this. This one's more face on, and this one's at a different angle too. And so we saw that there is a huge variance in their sizes and brightness. So they're much different masses. And then we also looked at the binary population. So binary means that there are two stars forming close to each other. And this is interesting to think about a planet forming around two stars because we don't know what the implications are for that. But you see the same thing here, that we have different sizes, different brightness for these disks. You might also notice this doesn't look like there's two stars there. So you might think I'm pulling a fast one on you, but actually this is what we call a circumbinary disk, which means that there are two stars that have a disk surrounding both of those stars. And one important outcome of this paper was that the binary stars actually have a smaller disks than the isolated stars. Okay, so the binary stars are next to each other. They're rotating around. They might have dynamical interactions with each other, but we tested to see if it was due to the companion star was like ripping away the material. And they're actually smaller than they should be due to that. So we don't know why, but it was interesting to find. And then we also had some triple stars. So I don't know if there's any science fiction fans here who might have read a book called The Three-Body Problem. If not, and if you're interested in astronomy, I highly recommend it. It's really interesting. But you start to get weird dynamical effects once you have three massive bodies. There's no stable orbits. So this brings into question, if planets form around stars like this, what does that mean about the type of life that could live there? Because you can't predict how the three bodies are actually going to be orbiting. So you might get really close encounters where the star comes really close to the planet and could rip away the planet's atmosphere. So those are shown up here on the top. You might notice there's always a binary and then another star that's close by. But my favorite from this survey was that we saw these footprints in these disks. And remember, the HL tau image that I showed you from Alma, so this is another Alma survey, was 10 minutes of integration time. So they looked at the protoplanetary disk for 10 minutes. And this was only in 30 seconds that we were able to detect this level of depletion. So you see here, there's like this hole here. You see here, there's like this outer ring. There's a hole right there. So that was just a testament for how powerful this telescope is. So that's a great question. We didn't ask for more time. So when you're observing, when you put in time for these observations, you write a proposal months in advance to when they actually do the observations. And you ask for the time that you think you need. These results were actually really surprising to us. We did not expect to see these rings and gaps. This was one of the first results that showed that this is common and that we should actually expect this in most of our observations if we look at it with high enough resolution and with enough time. So some people have done that. So this is the DSHARP survey done by Sean Andrews, where they chose 20 protoplanetary disks to look at with ALMA at really, really, really high resolution. So this here is what their resolution is. So it's different for each disk, but you see here, that means that we can look at really, really, really fine detail in these disks. And you see that there is a ton of substructure in these objects. You can tell here, there's some like really wide gaps. If you look really hard, you can see some like ring-like structures in there. Up here is pretty cool. So these look like spiral arms. So really kind of analogous to galaxy observations. And we see, you know, like just, wow, this is an amazing data set. This looks so cool. And we see all of this indirect evidence for planet formation. But what can we do with this, right? Like, it's great. We're looking at really pretty pictures, but we want to do some sort of science with it. And so what we can actually do is we can look at the location of these gaps in these disks, and we can map out where in the disk it occurs. So how far away from the star is it? We can also use the width of, we call this depletion because we don't see any dust there. We can use this width to estimate how massive the planets must be. So you can think about it, if it's kind of a little small dinky planet, it shouldn't create a really wide gap, right? If it's only like getting some of the disk material, it should be a pretty narrow gap. But if it's a big, massive planet, then you would expect a lot of the surrounding material to be eaten up by this planet. So we can start to make estimates for how big the planets must be that are forming in these disks. So some other people decided to look at the Alma Archive and just see if they could see this, because like I said, we weren't expecting this, but maybe there were observations that people just hadn't looked at. You know, sometimes you propose for data and you don't do anything with it, or you don't have time. So some people searched what we call the archive, which is just a list of all the data products that telescopes have put out. And they actually were looking for this substructure and to do some sort of statistical analysis on them. So this is 38 protoplanetary disks. And the cyan bar here is about 30 AU. Now, to put that into perspective, 30 AU is as close as Pluto gets to the sun. So Pluto has a really eccentric orbit, which means it's not circular like the other planets. So it gets as close as 30 AU and as far away as about 45 AU. So you can see that all of these planets, these rings, happen much further out than Pluto's orbit. And that's confusing because when we looked at the plot of exoplanets, we saw that most of them actually had shorter orbital periods than any of the planets in our solar system, which means that we would expect them to be forming much, much closer in to the central protostar. So we don't know why that is. Another thing that this team found was that they made estimates of the dust cavities. And what they found was that they're only about a fraction of an Earth's mass. So remember, we can only create the planets from the amount of stuff that we have. So why are they only a fraction of the Earth's mass, especially when most exoplanet systems that we see are much more massive than Earth is? So the caveat is that not every single one of these did show this result. So GG tau, which is here, was about a half an Earth's mass. And then where is WBS 60 here, was about 3.5 times the Earth's mass. But again, we're not getting to Jupiter mass sizes. So Jupiter is about 300 times the mass of the Earth. So we're really, really not accounting for all of this mass. We have this missing mass problem. So unfortunately, that's not solved. But I wanted to show you a picture of the first protoplanet that we have detected in one of these protoplanetary disks. So every few years, a paper comes out that says that they've detected a protoplanet, and it's very exciting. But what it usually happens to be is an image artifact, and other observations show that it's not truly there. Well, this PDS-70b is actually a bona fide protoplanet, and it is right here. So this is an Alma protoplanetary disk. Both this image on the left and in the middle is Alma. You see here, this robust value has been changed to try to eke out more from the data. Maybe this little blip is another protoplanet, but PDS-70b was confirmed to be a protoplanet using near-infrared observations. So this is shown here. It's offset a little bit from the Alma detection, which is these two red circles here. But pretty much what this means is that this planet exists, or this protoplanet exists. So that's incredibly exciting, and that opens up a whole new realm of observations that we can take to search for these. So what we can also do is we can look at protoplanetary disks, like the PDS-70 image was near infrared. We can look at them using near infrared wavelengths. So these are 9 protoplanetary disks from the Very Large Telescope, VLT. So astronomers aren't very creative in their names. They like to name things like very large or extremely large, things like that. So this is using near infrared light. And we see a very diverse set of protoplanetary disks in here. So if you recall from the cartoon image of the disk that I showed, the radio waves trace the mid plane of the disk. The near infrared actually trace these outer, like upper, what we call atmosphere, but it's not really an atmosphere, like the upper layers of the disk. So you can see here, unfortunately, the display is not showing, like you can also see, like on the computer, you can see some of the disk here, but it gives you an estimate of how tall the disk is. So we can see also some substructure in these disks. To the keen observer looking at this panel, you see that there is this like gray spot in all of these. What I didn't tell you is that when we're looking through radio telescopes, we actually don't see any stellar illumination. We don't see the star. The star is invisible. But once we start to go to infrared light, the star is no longer invisible. So we have to cover it up with a coronagraph. So that's just why there's like that little like blob in the center of these disks. And you may notice, these ones are really excellent observations. So we do see the ring-like structures in them, but not all near-infrared observations of disks show as much structure as the radio telescopes do. This is just due to stellar illumination. So the substructure is still there. We just can't see it. So finally, I want to talk to you a little bit about a problem that we are also trying to reconcile, which I alluded to, which is that the locations of the gaps don't occur where we see protoplanets. So this is an extreme example. This is the TRAPPIST-1 system. So all Earth-like planets, so pretty exciting. This was found around an M dwarf a few years ago. But you'll see here that its orbits can actually fit within Mercury's orbit. So if we're seeing the substructure at really far out radii from the inner star, what does that mean for what types of planets can form? So we have to reconcile that. So again, this is the disks that we saw in my Ophiuchus sample that showed these footprints. So just to show you how we actually figure out where these gaps occur, we take an average. So you can imagine if you average what we call azimuthally, and you collapse it into one dimension, and then you have the flux on the y-axis and the disk radius on the x-axis, you see in this OF8 that this gap occurs at about 85 AU. We're looking at about 57 AU, and this one here is at about 145 AU. So again, remember, Pluto, the closest Pluto gets is 30 AU, and the furthest that it gets is 45 AU. So we really need to reconcile why the gaps that we see in these disks are so much further than the orbits that we measure of our exoplanet systems. And then I told you that there is gas and dust in these disks. I only look at dust emission. Dust emission is much easier to detect. But actually, these disks have more gas than they have dust. Dust only accounts for about 1% of the total mass. So this is just brief to show you how you would look at gas in a disk. So this is CO observation, so carbon monoxide. And with the gas observations, you can trace the motion. So these are broken up into different velocity bins to try to understand how the disk is rotating. So this is IM loop. It's a disk in the Lupus molecular cloud. And using these observations and seeing at what velocity channels had more or less emission, out that this is how this disk is spinning. So we're really learning about the demographics of these protoplanetary disks where these planets are forming. But we still have quite a few questions. Remember, our disks that we've looked at are not massive enough to account for the exoplanet population that we see. So we know that planet formation must take place by the class 2 stage. But what if it happens earlier? What if right when the star is starting to form, in that class 0 phase, we start to form planets then? That might account for why we're not seeing enough mass in the disks to make these Jupiter-sized planets. There's also a possibility, so we've been treating these disks like they're isolated, that they're not part of this larger molecular cloud, this environment that has gas and dust in it. So it's true that these class 2 protoplanetary disks deplete their natal envelope, but they still have some diffuse material hanging out that could somehow be funneling material onto protoplanetary disks. And so maybe we can look at those mechanisms. And then finally, new instruments are coming online. So I don't know if you've heard the James Webb Telescope successfully launched on Christmas. So that was really exciting. That will get extremely high angular resolution, which means that we'll finally be able to look really close in to the central star and understand what's happening there. There is also the NGVLA, so this stands for Next Generation VLA, that will have really excellent resolution that will be able to take radio observations of this inner disk. So maybe we'll actually be able to see if we see these footprints there as well. So we don't have, as powerful as ALMA is, we don't actually have good enough resolution to probe, especially where a TRAPPIST-1 system would be forming. And so if you take anything away from my talk tonight, I want you to take these two things back with you. No exoplanet system that we have observed matches our own solar system in its architecture. So this means in its planetary mass, size, or orbital structure that we see. Our understanding of planet formation has truly exploded in the last decade with the use of telescopes like ALMA. But however, we still have a ways to go before we can actually reconcile planet formation with the exoplanet systems that we see. And the instruments that we need to actually reconcile these observations are coming online soon. So thank you. Questions for Dr. Cox?
So at the very start, it showed there were a lot more gas giants and other planets. There wasn't a lot of terrestrial planets.
Yes.
Do you know why?
Yes. So I'll go back to that plot, or here I will. Yes, so that's a great observation. The reason for that is due to the way that we detect exoplanets. So we have two main ways of detecting the exoplanets, radial velocity and transit. Oh, so I forgot to say for the people who are watching over YouTube, someone asked why we have more gas giants detected than terrestrial planets. So radial velocity and transit are the two ways that we really have been observing exoplanets. So radial velocity means that you have a massive planet that's orbiting its star that's massive enough to create this like wobble in its basically light curve that you plot. So you have to have a massive star or a massive planet in order to detect it using radial velocity. And then transit, so this is the way that Kepler detected exoplanets, is when we observe the star and the planet's going over, and then the planet passes in front of the star and we see a dip again in the light curve. So you can imagine you need a large planet to block out enough of the star's light. And so our instruments are becoming more sensitive. We can find smaller planets that way. but it's difficult, right? It's much easier to see, especially a hot Jupiter. So a Jupiter-sized planet that's really close to its host star, that'll block out a lot more light than, say, like an Earth-sized planet. Mhm.
Is there a way to characterize the orbital periods of protoplanets just from looking at the dust line?
Okay, so the question was asking if we can characterize the orbital periods of protoplanets using the dust lanes. So not that I know of.
Is there any theory about whether or not those are consistent?
Yeah, so the question was asking if we expected the orbits of the protoplanets to change. And yes, we do actually. So we can have what's called migration of planets. So the planets don't have to stay in one spot after they've formed. I believe, I don't know if it's still the leading theory of the solar system formation, but it at least was a few years ago, is that Jupiter actually formed beyond Saturn's orbit, and they switched places somehow. So they can move around in the disk. They're not stationary there until I guess they get into a stable orbit.
So these protoplanetary disks that were found in surveys, in which there was missing mass, are we just not sure where that mass came from, or there's, I guess what I'm asking is, are those protoplanetary disks that's all the mass that they're going to have for their form solar system, but like a planet or two that's like a quarter the size of Earth, and that's it.
Yeah, so the question is whether or not the protoplanetary disks will just form really small planets if the mass is what we estimate it to be. And so I think that's what we're trying to find out now. We're trying to understand if our mass estimates are correct. So we have to model the mass. So there's always like errors that can be in the model. We also, we don't know if maybe the planet started forming before the disk was really visible. So in like these earlier phases of the protostar's life, which means that they might have accumulated more mass than we're accounting. And then, like I had said, there's a possibility for perhaps funneling some of the clouds material onto these disks somehow, and then providing like a mass, like more mass to the disks, even though the disks are less massive, like somehow funneling the material that's out here into them. But if the protoplanetary disks are actually only that massive, then yeah, we can only form small, like dinky little planets. Yeah.
If the stars forming, I'm sorry,
no, that's okay. So were you asking about the age of, yeah, so about the age of the protoplanetary disks?
compared to the stars being formed.
So the sun and the earth are approximately the same age. Yes, so around 5 billion. You know, they might differ by a few 100,000 years, but yeah, they're approximately the same age.
So our sort of brief encounter with Oumuamua, that extrasolar object a few years ago, I think it kind of made us have to look again at what we think is in the interstellar medium. And you showed those, you showed all those different images of protoplanetary disks where, sorry, protostellar disks, where the outer perimeter was way, way, way outside, sort of where Pluto is for us. Is there any way that any of that dust and gas would eventually work its way out of the forming star's gravity well, or is that just not physically reasonable?
Yes, so the question was asking about the extrasolar object. I'm gonna butcher the name, with Oumuamua, sorry, but Oumuamua. Yes, so asking about whether or not we expect the material from the protoplanetary disk that's out further than what we see as Pluto's orbit, if that can basically detach from the star's gravity. And the answer to that is yes. So we do expect even some like free floating planets. And I think that there is at least one free floating planet that we know of. I don't know what its name is. I know this because NASA has these like travel posters, like acting like you're going to travel to an exoplanet. And there's one that's always nighttime because it doesn't have a host star.
Thank you.
Yeah.
So is it possible for Kuiper belts to ever turn into a protoplanet eventually?
So the question was asking if the objects in the Kuiper belt can actually ever turn into a protoplanet based on collisions. And my understanding is that we don't expect it to. So I don't want to say no, because I don't know that, but I don't think we expect it to because I don't think it's actually dense enough. So protoplanetary disks are really, really dense. And even though it looks like the Kuiper belt is dense, comparatively, it's not. But I don't want to say that it couldn't like ever happen, like maybe under some like circumstances, specific ones.
The question on YouTube right now. So, yeah, go ahead. One more question. So, you put this paper. There was a limit to how far out relative to exoplanets, out 1,000 light years.
Yes. So the question was regarding how far out we could detect exoplanets using these methods. And yes, so Kepler and TESS do have a limit as to how far out that they're looking. I think you said 1,000 parsecs, 1,000 light years. Okay, so 1,000 light years would be about 300 parsecs. So yeah, so if that's true, and I believe that it is true that there is a limit to how far out these telescopes go, maybe we're just not looking far enough. But again, you can imagine that those would be really difficult to detect because we already have to have really sensitive instruments to detect the light that a planet blocks from its host star. So as we get further, things get dimmer, which means it's much harder to detect that like transit.
How far out is Alma
So most of the surveys on protoplanetary disks have been within 500 parsecs. So that's 1,500 light years. So a light year, if you're unfamiliar, is the distance that light can travel in a year. So Alma can look out to basically Orion, the Orion Nebula, and that's about 450 parsecs from us. And it doesn't get great resolution there. But we're interested in protoplanetary disks in Orion because Orion probably actually more matches what the solar system went through. So a lot of these surveys have been on low mass stars. Orion has some high mass stars. And so we're really interested in what the high mass stars do. That's a whole other beast. So high mass stars produce a lot of radiation, a lot of UV radiation, which can produce these intense winds and really affect how stars and planets form. But if we truly want to understand our own formation, then we have to look somewhere that's more analogous to like what we began with. But we're lucky that there's not a lot of massive stars close to us, because that would probably have some implications for what type of life could actually exist on Earth. Because as we know, UV radiation is not good for our own beings.
So did I understand you right that there's one exoplanet that's left its host star called the night planet? And so how did we find that one?
You know, I don't. So the question was asking how we found the night star, and I don't actually know. I don't know if you know.
Microlensing probably.
Microlensing, okay.
So sometimes these distant planets will actually pass in front of the background star, and their gravity from the planet will actually cause the light from that background star to divert toward the Earth. That background star will suddenly appear bright over the course of several days or hours. They don't seem planet directly, but we can see its gravitational influence. Yeah, I guess PSR something like that. It's really long, man. I know what you're talking about.
Yeah.
Well, if there are no other questions, let's see if Dr. Cox is going to respond to them.
And it looks clear out, actually. So if you're interested in joining us up at the observatory, we're going to try to do a little stargazing tonight. Probably not too long, but we will do a little bit tonight. I will say, if you've not been up to the observatory before, it's not handicapped accessible, I'm afraid. So if you have trouble going up and downstairs, we'll have to make other arrangements for you. But if you're interested, feel free to hang out in the lobby for a few minutes while we get things set up.